Let's talk about the mole and how it relates to chemical formulas and reaction equations. Okay, so for example, if I have a molecule of methane, CH4, okay, in this molecule I have one atom of carbon and 4 atoms of hydrogen, right? So that means that I have a 1:4 ratio. I always want to say ration when I write the word ratio. I don't know why, but 1:4 ratio. So keeping with that ratio, if I'm talking about a mole of atoms, then I can say the same ratio as it relates to moles. So I have 1 mole of carbon and 4 moles of hydrogen, which still keeps my ratio. Right? If I look at it in a chemical equation, a reaction equation, let's talk about the best one. Right? I can say that I have on the reactant side, I have 2 moles of H2 and 1 mole of O2. Okay? Because it's all about ratios. I can say that I have 1 molecule of O2 and 2 molecules of H2, but if I scale everything up to the level of moles, then that means that I have 2 moles of hydrogen and 1 mole of oxygen, and I maintain my same ratio. And on the product side, that means that I have 2 moles of water. And this is going to be the most common thing that we deal with chemical equations, with reaction equations. So what's beautiful about this is because it's all ratios, we've talked about ratios before and how they can be used as conversions. Okay, so given this information, I can write a ratio of one thing to any other thing in that equation. So I can relate one thing to any other thing and find out how much there is. So I can write these as ratios like this. I can say 2 moles of hydrogen to 1 mole of oxygen. Or I can flip that. Or I could say, depending on what I want to know, 2 moles of water for every 2 moles of hydrogen. Or I could say 1 mole of oxygen to 2 moles of water. Okay, and I can flip those. They're conversion factors. So if I have hydrogen and I want to find out how much oxygen, I just take that relationship and put hydrogen on the bottom and cancel things out. Just like we've done with all the other conversion factors so far this semester. Okay, so we're going to be using these coefficients in the reaction equation to make conversion factors. Okay, remember this lack of a coefficient means that there's 1 O2 there. So let's put this to practice. All right, we've already talked about percent mass or percent by mass. So now we're going to extend that idea and start talking about percent composition. And in this case, we're talking about percent composition by mass. Right? And so the basic idea when we want to calculate percent composition, our basic form, is mass of the part divided by mass of the whole times 100. Okay? Or mass of the component divided by total mass. Okay, both of those things mean the same thing. So let's do an example. What is the percent composition of our molecule is C2H-Br-Cl-F3, which is probably an entirely made-up molecule. When I wrote these notes, I probably fabricated that out of thin air. Wouldn't know the first thing about how to name that sucker, but this is all for practice, all right? So in order to find this out without any other information, I'm going to use molar mass. Okay? If you had more information, you could say, what is the percent composition of 5 grams of this compound? But since we're given nothing else, we can always go to the molar mass. And if I want to calculate the molar mass of this monstrosity, C2H-Br-Cl-F3, I'm going to add up the molar masses of each atom, so the mass of 2 carbons, 1 hydrogen, 1 bromine, 1 chlorine, and 3 fluorines, and we come up with a molar mass of 197.38 grams per mole. Right? This is the total mass, okay, or the mass of the whole, total mass for 1 mole of this compound. Right? So in order to find out the percent composition of any one thing in there, I need to know the mass of each of the parts. Okay, so I know that I have 2 moles of carbon, 1 mole of hydrogen, 1 mole of bromine, 1 mole of chlorine, and 3 moles of fluorine, okay, from the formula. All right, so I can take the molar mass and calculate grams for that many moles. Okay, so I'm going to go through that process for each one of these components. So if I have 2 moles of carbon, and the molar mass of carbon is 12.01 grams per mole. Grams of carbon per mole of carbon. Okay, seeing the pattern here, we're going to keep doing this, using molar mass and ratios as conversion factors. So my moles of carbon go away, leaving me with grams of carbon. So in this compound, for 1 mole of compound, I have 24.02 grams of carbon. I have 1 mole of hydrogen at 1.0079 grams per mole, grams of hydrogen per mole of hydrogen. I have 1 mole of chlorine. Now remember, I'm getting these numbers, these molar masses, straight off the periodic table. Okay, I'm looking on the periodic table, and the atomic mass is the same numerically as the grams per mole. Okay, so 1 mole of chlorine from the periodic table is 35.45 grams of chlorine per mole of chlorine. We have 1 mole of bromine. Straight off the periodic table is 79.90 grams of bromine per mole of bromine. Moles will cancel, leaving me with grams of bromine of 79.90. And lastly, we have 3 moles of fluorine. And from the periodic table, fluorine is 19 grams of fluorine per mole of fluorine. So moles will cancel, leaving me with grams of fluorine equal to 57. Okay, so now I know the masses of all the parts, I can easily calculate the percent composition of any one of them. So let's say, what is percent composition of carbon in this molecule. Okay, remember our mass of the whole was 197.38 grams per mole. And my mass of the carbon by itself, mass of the part, is 24.02. So mass of the part divided by mass of the whole. So percent carbon, 24.02 grams of carbon divided by 197.38 grams of the compound times 100 means that we are 12.17% carbon. Okay, so anytime you need to do percent composition, you need to know the mass of the part divided by the total mass, or the mass of the whole. Okay? So I'm going to go ahead and stop this video right here, and we'll pick up on the next video talking about empirical formulas.